Hello, welcome to another session of Engineering Economics. In this video we will talk about arithmetic gradient and geometric series. So let's start with the arithmetic gradient. In many occasions we want to consider a situation in which the amount to be paid or to be received changes through time by a fixed amount, and this fixed amount we're going to call it G for gradient. We're going to denote it with G for gradient, and the cash flow series looks like the diagram that we have here. The formulas that we would be computing typically in a problem, we will have a present value or maybe a future value, and then we will have a series of annuities. The typical series of annuities of course goes from the first period till the end period. In this example, n equals 9. And then starting on the second period, the second cash flow, we have the effect of a gradient that it's added to the total amount to be paid. Now this gradient occurs, as you see, for the first time at t equals 2, and then at t equals 3 the gradient will appear 2 times, and then at t equals 4 3 times, and so on, all the way to t equals 9, in such a way that the last one, if in this example is t9, now g occurs 8 times. So this looks like a linear model in the sense that we can trace a straight line that put together all these points. Additionally, things that you need to take into consideration is that the first instance of the gradient is at t equals 2. The last instance of the gradient is at t equals n, that is for the n payments that you would have if you have an annuity. And the model with the formulas that we compute make a relation between the gradient, which is or the gradient series, which is the arrows that are depicted in red, to the p, which could be part of the solution. The gradient formula does not take into consideration the annuity because the annuity has its own formula. One more thing that you need to consider is that the gradient could have a negative value in such a way that maybe the first payment is larger and then it's decreased by the same fixed amount every time. The computations for each one of the cash flows can be done. In other words, you can compute how much it will be paid in any particular year as the annuity plus a certain amount of times the gradient, and since the first cash flow happens at, or the first gradient happens at t equals 2, then the equation turns it to be g times t minus 1. That is going to give you how many times, t minus 1 is going to give you how many times that gradient occurred, and to that we add the annuity, and that gives us the total cash flow for that particular year. Now, the formulas that we can use are depicted in these equations, and you have P given G to make the relation from the gradient to the present, or to obtain the annuity given the gradient we have yet another form, and finally we have the future. If we have the gradient, we still have yet another form. So with these results, we can proceed to try to solve a problem. Okay, so let's consider an example in which we're interested in knowing the present value of a series of cash flows. Let's consider that the gradient is $100 and the annuity is $1,000. $1,000, and the number of payment is 6, and the interest rate is 10%. So the equation that would define this problem is P should be equal to the gradient, which is 100, times P, given that I know the gradient, with the interest rate of 10%, and the number of periods being 6, plus 1000 times P given A for 10% and 6 periods. Okay, so all we need to do is we need to plug in these values for 10% and 6 in the formulas that we have for P given G, and the number that we would come up with would be 9.6842. Please check it in your using your own calculator. That's very important for you to practice. Times 100 plus 1000 times, now the factor here for P given A with 10% and 6, we have used this formula several times before, and the value is 4.35526. So the present value becomes $5,323.68. So we're going to solve more problems like this in other videos. Let's go to the gradient series. In the geometric series, it's a similar situation as what we had with the gradient, in which we might have an annuity, but now based on the first payment, the increments are not based on a fixed amount, but it's a fixed percentage increment or decrement with respect to the previous cash flow. So that means that the net effect of it is a nonlinear relation, because the effect of the gradient rate affects in a nonlinear way, because at every time the previous computation had increased or decreased, and therefore we have a nonlinear impact. In this graph that we have here, n equals n, and you can see that the first instance of the series also happens at t equals 2, but in this case we do not use the gradient per se. Everything depends on the annuity first. We also need to check here that the cash flow at any particular instance can be computed based on the first annuity times 1 plus j to the t minus 1, because everything depends on the first annuity. So okay, let's consider a geometric series with the following parameters. We have the interest rate being 10%, the first annuity is $1,000, the geometric series increases by 15% each period, and there are 6 periods. We are interested in finding the present worth. So the solution to the problem can be found by selecting P equals A1 times P given A1 for 10% as the interest rate, 15% the increment rate, and 6 periods. When we plug in these numbers into the formula, we obtain 6.11325, which we multiply times the first annuity 1,000, and the present value of this series is $6,113.25. Additional computations that we can obtain are the cash flow at any particular time. So for instance, if we have the cash flow the last period with a gradient, we have 1000 plus 100 times 6 minus 1. That would give us the cash flow at equals 6, which is 1500. And in the case of the cash flow for the gradient series, the last one at t equals 6 would be 1000 times 1.15 to the 6 minus 1, which would be 2011.35. So this was the theory on arithmetic gradients and geometric series. Check the other videos for the more sample problems.